Continuing on with our study of lenses, I'm now going to build on what we've already learned by focusing on focusing. Now this image here obviously looks unsharp, it's blurred, and this is caused by the fact that the lens wasn't correctly focused when it was taken. When we go to a correctly focused image, everything becomes nice and sharp. So this is what we're talking about when we're talking about focusing. So again, we've already covered some of this, but it's worth repeating it just so we get it clear. A 50mm lens, for example, is designed to sharply focus an object at infinity, and we're going to use the moon in this instance. Hopefully it's not at infinity, but it's close enough. So when it's positioned a distance of 50mm from the lens, and again we're using a simple lens. So a 50mm lens positioned 50mm from the sensor should give us a nice sharp image. And all other lenses obey this same principle. A 100mm lens would be 100mm from the sensor to give you a sharp image of something at infinity. So particles of light from each part of the distance seen, and again we're looking at a very, very small spot on the moon, for instance. In this instance, it's giving off light or reflecting light in all directions, and some of that is coming towards our lens. And from that one little spot, all these little rays of light then get focused onto the sensor at one little spot, and it's doing that for the entire image. But because of the scale of this image, or of this illustration, we can't actually accurately depict the way these rays of light are entering the lens. Okay. So if we imagine the moon is now a quarter of a million miles to the left, those rays of light are now effectively coming in at parallel to each other. Okay, all from that one little spot on the moon. So these individual photons, which are particles of light, each hit the surface of the lens at a different place, all around the entire diameter and surface area of the lens, all bringing it into a sharp spot on the sensor. So this is happening to every other part of the image, all the other part of the moon. It's all happening and building up to produce a full image on the sensor. So the amount that light is refracted by the lens, is determined by its focal length, and also by the distance from the lens's center. Okay, so light going through the center of the lens isn't refracted at all. Now going towards the edge of the lens, it's bent, refracted more and more. Now if we look at the very edge of the lens, for instance in this for this particular case, we could maybe say it's been refracted by an angle of 10 degrees right at the corners, the edges of the lens. It's refracted less towards the center and 0 in the middle. Now if we want the lens to focus at a closer subject, then those rays of light are no longer coming in parallel, or effectively parallel. Okay, so now they're now coming from, and remember those cones of light that I've been trying to depict throughout these videos? So they are essentially coming in more of a cone of light rather than parallel lines from something at infinity. But they're only going to get refracted by the same amount, that 10-degree angle. So in this instance, because the rays of light are coming in at an angle like this, they only get refracted by 10 degrees, the maximum here, and they all come together into a point behind the sensor. So those rays of light are actually being spread out over an area on the sensor like that. That is why it becomes a blurred image. So we can see from the diagram that if we could move the sensor to the right there, away from the lens, we could bring this closer image into focus. So this is achieved by physically moving the lens away from the sensor. In most cameras, moves it away from the sensor. But for this illustration, I'll just move the camera body. So you can see the camera body is moved, so the sensor is now at a position where those cones of light, rays of light, are coming in and sharply focusing it. Now these are illustrations from an old Olympus camera, and you can see that this lens, 135mm, focused at infinity, has that sort of size or length. When it's focused at its closest option, you can see that it's been extended. Okay, and as we focus closer and closer, we say that the lens is extending. We're extending the lens from the sensor, as in extension tubes, which radically extend the lens away from the sensor. And here we have some extension tubes, which were just basically hollow tubes with electrical contacts to maintain the continuity between the lens and the camera. But lenses can only be extended by a limited amount, which is why they all have a minimum focusing distance. You can't focus any closer. You'll also notice that now that we've moved the lens away from the sensor, it's actually a longer focal length lens. And so as you start to get closer, focus closer, you're actually magnifying the image a little bit as well. So the focal length of the size of the image reproduced changes as well. So the act of focusing by physically moving the lens away from the sensor until a sharp image is formed on the sensor, that is what we term focusing. That's what it's all about. Now these illustrations here are for the old type of manual focus lenses. Many of the modern lenses have got internal elements that carry out the same function, and so when you look at them, you don't actually get that physical change in size. Okay. So hopefully that's given you a little bit more of an idea of what focusing is all about, and now we'll move on to things like depth of field, which are how to implement some of this focusing understanding that we've just got.